So in the previous video where we discussed the mechanism of the dehydration of alcohols, we were discussing a very simplistic alcohol, symmetric alcohol, which was cyclohexanol. But what happens when the alcohol is a little bit non-symmetric? And this is where we're going to start using this rule defined by this Russian chemist called Zaitzev. So if we were to look at another example of an alcohol being dehydrated. Okay, let's look at this compound. So this would be 2-butanol. And to help illustrate this, I'm going to put in some of the hydrogens that are also attached to this molecule. We'll just go ahead and draw them out like this. I won't worry about this methyl group down there. So we discussed previously what the mechanism of this reaction is. And the initial mechanism is going to be the protonation of this OH group. So when we add our H+ catalyst, the OH group becomes protonated, and we would now have something that looks like this. Okay, and let me go ahead and draw in the other hydrogens, just so we'll be consistent. Okay, so like we saw before, now we've got this sort of water-looking molecule that can essentially now fall off. And what that's going to do, it's going to generate now the carbocation intermediate. Okay, so water is going to come off right there. Oops, let's draw that like that. And we get this carbocation intermediate. Again, let me draw in the fact that we now have these still have these hydrogens attached. And those become important when we start talking about the mechanism and the ultimate product that we get. So we have this carbocation intermediate. Let me put that in brackets just to indicate that it's a very short-lived intermediate. And now there are actually two possible ways that this could form an alkene. In the previous section, we talked about how we need to abstract one of these adjacent protons to now introduce a double bond, so and thus regenerating our catalyst. So here, let me go ahead and abstract one of the protons that's going to be over here on this methyl group. So I'll just use water to do that. We're going to abstract that proton, and we'll call this pathway A. Okay, so this is pathway A. And notice that if I did that, it would introduce the double bond here between carbons 1 and 2. So my products from pathway A would look like this. Okay, I'd have a double bond at the end of the chain. Carbon 1, 2, 3, 4. So I'd form what's called 1-butene. That'd be pathway A. But notice there's an alternative pathway. Instead of pulling off the protons here on the methyl group, what if we pulled off an adjacent proton here at this carbon? So if I use water instead over here, pulled this proton off, and that now made a double bond here, we'll call this pathway B. That would now make a very different alkene. Okay, notice we would now have 2-butene. Well, it turns out when you go into the laboratory and actually do this reaction, and this is the type of reaction that Zaitzev investigated, you find, in general, there's always a favored product. And what Zaitzev did when he examined multiple different alcohols and did dehydrations was that this type of product was favored. Now, what's the difference between pathway B and pathway A's product? Well, let's look at the actual double bond. Notice that in this compound here, this is what's called a mono-substituted double bond. There's only one carbon group coming off the double bond. So this is called mono-substituted. Conversely, the one that's favored, notice that in the double bond, it has one group here and one group here coming off the double bond. So this would be a di-substituted double bond. So in general, if we were then to write out Zaitsev's rule, okay, so again, Zaitzev, after going through multiple different reactions like this, he always seemed to find that the more stable or the more favored product was the compound that had more substituents coming off the double bond. All right, so let's just write that out. So Zaitsev's rule, when dehydrating an alcohol, the more substituted carbon-carbon double bond is favored. Now, in our class, you're not going to be expected to know like how much is it favored by, but just to give you an indication that if you were to run this reaction in the laboratory, this one might form about 80% of the product, whereas the mono substituted might only form 20%. So when we talk about a favored or major product, those are the kinds of ratios we're looking at. We're not talking about 100% versus 0%, and that's certainly the case with just about all alcohols. So again, Zaitzev's rule, just to summarize then, would be when you're dehydrating an alcohol, if there are two possible options, you'd want to then look at which product gives you the more substituted carbon-carbon double bond. In the next little section, we'll take a look at a couple more examples to get some more practice with Zaitzev's rule. So to finish up our discussion of Zaitzev's rule, let's just do a couple examples that'll give you some practice at applying Zaitzev's rule. Let's look at the dehydration of 2-methylcyclopentanol. So if you were asked to predict what's the major product of this, so using H+ catalyst and heat, let's just draw out the two possible products. So when you're doing a dehydration reaction, obviously the OH group is going to be removed. And let's just go ahead and draw in the adjacent hydrogens. So when I say adjacent hydrogens, I'm meaning the hydrogens that are on an adjacent carbon relative to the original alcohol carbon. So this is the alcohol carbon here, and we look at the two adjacent ones there. So if I removed one of these protons up here, the product would be this. So I would get what's called 3-methylcyclopentene. Conversely, if I removed this proton here and introduced a double bond between or next to the methyl group, I would get 1-methylcyclopentene. So if we were basically trying to evaluate or figure out what would be the major product of this, if we applied Zaitzev's rule, again, his rule states that when dehydrating an alcohol, the favored product is the carbon-carbon double bond that has more substituents on it. So if we look at this carbon-carbon double bond up here, this is a di-substituted, so only two substituents, whereas this one is tri-substituted. Okay, so it's got a methyl group and the two carbons of the ring, whereas this one only has the two carbons of the ring. So if we were to predict what would be the major product, it would be this one here. Now again, you're not expected to know what the exact percentages of these are, but this one certainly would be favored. Let's do one more example. And I'll draw it maybe a different way. You'll often see this as either H+ catalyst, or maybe they'll actually tell you what the acid catalyst is, in this case H2SO4. So looking at this, let's now draw in the adjacent hydrogens, just so we can kind of draw out both possible products and then decide which one's going to be favored. So there are two hydrogens here, and then these two methyl groups are equivalent. I'll just go ahead and draw the hydrogens on this particular methyl group. I could have done it here, doesn't really matter. So if I were to deprotonate one of the protons out here on this methyl group at this position, I would introduce the double bond here as water would be removed. And I would get that product. Okay, so again, that would be if I remove the OH and this proton, I would introduce a double bond here between carbons 1 and 2. Conversely, if I remove the proton here from this middle position and this OH, I would introduce a double bond in the middle of the molecule, and I would get a compound like that. So again, if we look at the substitution patterns of these two products, this one is only a di-substituted double bond. There's a methyl group here and then another alkyl group. So that's di-substituted. Conversely, this one is tri-substituted. So there's a methyl group, and then this ethyl group here. So the favored product, applying Zaitsev's rule, would be the tri-substituted carbon-carbon double bond. I haven't gone too much into the rationale or the reasons why Zaitsev's rule worked. The bottom line deals with the stability of the products. In general, more substituted double bonds tend to be more stable than the less substituted double bonds. So please get some practice in terms of homework problems, applying Zaitsev's rule to the dehydration of alcohols, a very, very important reaction in organic and also in biochemistry. Good luck.